This lecture talks about one of the most important topics of the subject, so you should be more attentive. Otherwise, you will commit silly mistakes while solving problems. We have a simple energy band diagram where EC and EV are the minima and maxima of energy levels considered to be present within the conduction band and valence band respectively. But if you think that there is a guarantee of finding the same electrons at the same place at all times, then it is merely a misconception. Another misconception is that there are no electrons present between conduction band and valence band. Even if the crystal is kept at fixed temperature, then also the occupancy of a state by an electron is probabilistic in nature. In quantum mechanics, while determining the statistical behavior of large number of particles, we consider the behavior of the group as a whole rather than behavior of each individual particle. There are few distribution laws which tries to determine the distribution of particles among the available energy states, like Maxwell-Boltzmann probability function, Bose-Einstein probability function, and Fermi-Dirac probability function. Fermi-Dirac probability function is the most widely used function, at least for the study of semiconductors, and as an electronics engineer, we should have in-depth understanding of this function. Even though in all the three functions, particles are considered to be indistinguishable, but in Fermi-Dirac probability function, only one particle is permitted in each quantum state, whereas in the other two functions, there is no limit to the number of particles permitted in each quantum state. We can write Fermi-Dirac probability function as 1 upon 1 plus exponential E minus EF divided by kT, where K is the Boltzmann constant, T is temperature in Kelvin, E is the value of the energy band at which we want to find the probability of finding an electron, and EF is the Fermi energy level. Fermi-Dirac probability function gives the probability of a quantum state will be occupied by an electron or not, even for a small fraction of time, like the electrons who are trying to make transition from valence band to conduction band. The significance of Fermi energy EF is very important. Now let us find the probability at Fermi energy level EF. You can see that EF minus EF will give 0, and the value of E raised to the power 0 is 1, which will give the final value of the expression to be 1 by 2. It means that at Fermi energy level EF, the probability of finding an electron is 1 by 2. This gives us the first definition of Fermi energy level, which states that Fermi energy level is the energy level at which the probability of finding an electron is 1 by 2 irrespective of temperature. As you can see, when the numerator of the exponential term is equal to 0, then whatever is the temperature, it always gives the value of exponential to be 1. Now, we will find the probability of electron at different energy states at 0 Kelvin. At 0 Kelvin, we have two cases. Case 1 is when the energy E is greater than Fermi energy level. You can clearly see that when temperature is 0 and E minus EF is positive, then the whole exponential expression will come out to be infinity, giving 1 upon 1 plus infinity, which finally results to 0. And the second case will be when the difference energy is smaller than Fermi energy level. Now, in this expression, we know that T is 0 and E minus EF is a negative value, which will give us E raised to the power minus infinity, resulting into 1 upon 1 plus 0, giving the final value to be equal to 1. It means that at 0 Kelvin, all the energy states above Fermi energy level are vacant, and all the energy states below Fermi energy level are filled with electrons. This gives us the second definition of Fermi energy level, which states that at 0 Kelvin, Fermi energy level is the energy level above which all the energy states are vacant, whereas all the energy states below it are filled with electrons. One more important point is Boltzmann approximation. In Boltzmann approximation, we assume E minus EF is several times greater than kT, meaning that in the denominator of the Fermi Dirac probability function, the exponential term is significantly greater than 1. Therefore, the Fermi Dirac probability function then modifies to exponential EF minus E divided by kT. You must remember that this is a result which is provided by Boltzmann approximation after making an assumption that E minus EF is several times greater than kT.